Hello everyone, this is May. In this presentation, I will talk about modeling petroleum generation, retention, and expulsion from the Vaca Muerta formation in Argentina. First of all, I would like to thank my advisors at Stanford University and at Total. This work is part of my postdoc research work at Stanford University with Basin and Petroleum System Modeling Group, and this project is sponsored by Total. The objective of this study is to improve the understanding of petroleum expulsion and retention from source rocks through basin modeling integrated with compositional kinetics and retention modeling. We use Vaca Muerta in Neuquén Basin as an example. To achieve the goal, it's important to study the effects of key mechanisms and variables, and in this presentation, we focus on the generation and retention model. It's also important to calibrate the model using the key measurable parameters, such as temperature and fluid composition and properties. Neuquén Basin is in the central west Argentina and bounds to the west by the Andean volcanic belt, and it was evolved through three tectonic stages. Firstly, rifting in Triassic to Jurassic, followed by a thermal subsidence in Jurassic to Cretaceous, and then evolved to a foreland basin followed by an uplift in Cretaceous to Neogene. And the data we used to build the model and constraint uncertainties are summarized here, including 18 depth maps interpreted from seismic and stratigraphy and controlled by over hundreds of wells. And in this study, we focus on the Vaca Muerta sequences and using the data from 8 wells as shown here. Figure on the left shows a lithostratigraphy of the study area in Neuquén Basin, and the Vaca Muerta formation was deposited in late Jurassic, Tectonic to early Cretaceous variation. It was deposited during the thermal subsidence stage, and figures on the right shows the Vaca Muerta Facies distribution, and the lower Vaca Muerta was deposited during the marine transgression under restricted circulation, and that associated with the basinal marine shale that is massive and also organic rich everywhere in the study area. And the variation upper Vaca Muerta was deposited in a regressive marine environment that is an open marine and associated with various little fishes in our study area, including the basinal marine shale as well as marginal marine and carbonate platform, and that associated with heterogeneous organofiscal distribution as well. So in this study, we focus on the lower Vaca Muerta to study the source rock kinetics and their generation and expulsion retention history. Here shows the modeled lower Vaca Muerta immature kerogen that fit on the trend of measured global data. Specifically, as shown by the red rectangle here, the modeled lower Vaca Muerta immature kerogen has an HI value around 700 and has a hydrogen to carbon ratio around 1.27, and this is comparable to the measured data in our study area as well, as shown on figure on the right. Here shows the HI values of measured lower Vaca Muerta source rocks at different locations in our study area, and the immature sample has an HI as high as 800, and then through thermal maturation, the HI values decrease. And the modeled Vaca Muerta, lower Vaca Muerta kinetics prediction that agrees well with measured data. A 3D basin model was built with the dataset with 17 stratigraphic layers, including 6 Vaca Muerta upper Vaca Muerta layer and 3 lower Vaca Muerta layer, and different fishes for each sequence were incorporated into the basin as well. And for example, in here we can see the upper Vaca Muerta shows a progradation pattern from the southeast to northwest, and that incorporated the Facies variation from the carbonate platform to marginal marine to basinal marine, from the southeast to northwest. Well, in the lower Vaca Muerta, it's a condensed section with more homogeneous basinal facies almost everywhere in the basin. And for each little facies that meets the lithologies with fine-tuning the facies related parameters were modeled as well, and that focusing on the substratal compaction. And also the TOC, initial TOC maps and various HI values for the 9 Vaca Muerta layers were applied. And in addition, the erosion model, we tested different erosion scenarios, and in general, there were more erosions in the west than in the east, and erosion timing are likely since about 15 million years ago. And this study was based on sonic logs and epitaph feed tract analysis to estimate the quantity and timing of erosion. The map-based boundary conditions of key layers and associated with the paleogeography were applied for the Basin model and to build the base case model. And then the different scenarios of heat flow history associated with different tectonic stages and the different erosion timing were tested. For example, here shows a plausible scenario of the heat flow history at well 7, and we can see after the rifting during the thermal subsidence and first stage of foreland building that the heat flow decreased continuously and then until it reached the maximum barrel followed by an uplifting, the heat flow increased rapidly to reach present day's condition, and then the maximum barrel heat paleo temperature and present day temperature were calibrated using the epitaph feed tract data and corrected bottom hole temperature. The barrel and thermal model are calibrated, and here shows some of model results. Figure on the left, upper left is showing a thermal maturity map of the lower Vaca Muerta sequence 20, and that shows in general it's more mature in the left right now in the gas window, and it's less mature in the east and southern edge of the basin, which right now is in the oil window. And the insert table is showing the comparison between the modeled visionary reflectance EZRO compared to the measured mean RO and its equivalent. And the results are very comparable. And figure to the right is showing example of at well 7 of the thermal maturity and temperature calibration depth profile. And figures on the bottom is showing the thermal and barrel history. Figure on the bottom left is showing the the barrel curve of each layer and overlaid by thermal maturity. When we use sequence 20 as an example as highlighted here, it was buried since late Jurassic to early Cretaceous, and it entered the oil window since around 130 million years ago and remained in the oil window till about 50 million years ago, that is at the beginning of the Eocene. And that associated with the increasing transformation ratio of the kerogen and increasing temperature and visionary reflectance as shown on the right figure. And through continuous barrel, the temperature and the visionary reflectance continued increasing. That the lower Vaca Muerta entered the gas window, that oils continued to crack into the gas components. until it reached maximum barrel at around mid-Miocene, that followed by a quick uplift, that the maximum barrel was reached in mid-Miocene and followed by a cooling stage. A 17-component kinetics was built and incorporated into 3D Basin model using Petroleum software. And here shows the modeled results of the primary and secondary cracking in a closed system. We can see through increasing the temperature that various facies were generated and then cracked down in the system. So when we integrate the basin modeling with compositional kinetics as well as the preferential retention model that simulate better, more closer to a natural petroleum system with expulsion and retention. Here shows an example of the using the integrated basin modeling with the compositional kinetics and retention model to study the petroleum retention and expulsion history and mechanisms. So the time plots here are from the lower Vaca Muerta in well 6 with the present day regional reflectance around 1.5% RO, and through continuous burial with increasing the thermal stress that the kerogen entered the oil window around 130 million years ago, and that associated with the regional reflectance around 0.7, that through primary cracking, petroleum generation increased and the sorption capacity decreased. When the total generation is less than the sorption capacity, that all the total generation will be or retained within the source rock, and as forms of sorption as well as free retention in the pore space of the source rock, until around 90 million years ago, that associated with regional reflectance around 0.9% RO, that the total generation of petroleum exceeded total sorption, and that expelled the exceeding petroleum to the pore space of the pore space of the source rock as free retention, as well as the expels it out of the source rock into the carrier beds, and that is the first stage of the petroleum expulsion. And this first stage of petroleum expulsion continued to about 50 million years ago at the beginning of the Eocene, that associated with the regional reflectance around 1.1 to 1.3% RO, that all the kerogen were consumed to generate petroleum, and also all the polar components were consumed to by secondary cracking to the lighter hydrocarbons. So, and this stage of petroleum expulsion is associated with the increasing of the pore pressure, permeability, and the organic porosity. And through continued burial, that thermal stress continued increasing, and secondary cracking of the oil to gas components that induced the volume expansion, that in turn induced the rock fracturing and second stage of petroleum expulsion. And this time, the petroleum expulsion followed by the further compaction, and that associated with the decreasing of the pore pressure and permeability and porosity. And through continued burial, that the secondary cracking of the oil components to lighter gas components continued, and that associated with increasing the pore pressure and the permeability again, and maintain the source rock in porosity until around mid-Miocene, around 15 million years ago, that reached the maximum barrel and maximum paleo temperature, and followed by uplifting and with temperature decreasing temperature and pressure that associated with the stop of the secondary cracking, and the porosity maintained to present day without further compaction. And here shows the calibration of the composition of petroleum retention and expulsion using the rock extracts and produced oil composition. And it shows that the modeled results are comparable to the measured data. And here shows the comparison of the modeled retention to measure the data using different kinetics. And as shown by black symbols and trend lines, the lower Vaca Muerta customized calibrated to the measured data that fit best to the measured data, and the published models have show larger discrepancies to the measured data, and this indicates the customized calibration is important to predict properly, and the modeled data modeled kinetics can be used to build the kinetics model as starter point, but if without further calibration, it may not predict properly. Here shows the results of the calibration for gas wetness. The modeled results are comparable with measured data that through continuous increasing thermal maturity at different wells, the modeled result follow the trend line of the decreasing wetness. This slide shows the calculated gas-to-oil ratio of the 3 oil wells and the condensate gas ratio of the 2 condensate wells, and compared to the measured data. In conclusion, the integrated 3D Basin modeling with the compositional kinetics and retention modeling improved the understanding of petroleum generation, expulsion, and retention history and mechanisms. And the model results indicate in the deeply buried area of the Lower Vaca Muerta in the western Yukon Basin, the petroleum expulsion started after the late Cretaceous and contained 2 stages. The first stage is due to petroleum expansion generation exceeded retention capacity, and the second stage related to the secondary cracking of oil to gas components that inducing fracturing and further compaction. And the less matured area in the eastern part of the Yukon Basin experienced the 0 to 1 stage of the expulsion. And in the mid-Miocene, the tectonic uplift stopped thermal stress and secondary cracking and decreased the pressure and temperature and maintained porosity without further compaction. And uncertainty study was also included in the model, and multiple key parameters were used to calibrate and constrain the uncertainty. And the workflow and insights can be applied to global and conventional oil and gas plays. This work was submitted to Marine and Petroleum Geology, and right now is under review. There are more details about this study. If you're interested, you can read the paper later in this year. Now, I would like to express our special thanks to Total Company for their sponsor on this project, and also thank the advisors at Total for their contribution and advice. And we appreciate Schlumberger for providing the Petromod Basin modeling software and for the advice in the technical support team. We appreciate advisors at Stanford University for their valuable advice, and thank the company affiliates for your support for Stanford BPSM, and thank you all very much for your attention.